Okay, next exercise 6. So here we are supposed to prove proposition 15, which if we recall says that when we are given a sequence of rational numbers, that is a Cauchy sequence, then being a Cauchy sequence it will have a formal limit. The proposition says that the sequence as a sequence of real numbers converges to that formal limit, because every rational number is a real number. We have to prove this, and also using this following outline which has been given here. So we have to show that the sequence converges to L. So we will start by assuming some positive real number epsilon, and then we have to show that the sequence is eventually epsilon close to L. We will assume for the sake of contradiction that this is not the case. The sequence is not eventually epsilon close to L. Using this assumption and the fact that the sequence is a Cauchy sequence, we will then have to show that there is some integer n greater than or equal to small m because that's where the index of the original sequence starts. For such a capital N, all the terms of the sequence an starting from that stage are either greater than L plus epsilon by 2, or all of them starting from that stage are less than L minus epsilon by 2. And then ultimately we have to use exercise 548, which we will see in time. Okay, so let us see the solution. Well, but before I write the solution down, let me say something. There is a religious function going on in a neighboring house. Okay, so every now and then there will be some noise disturbance. Since it won't be too much of a disturbance and we can manage, so I am continuing the video. Okay, just to tell you, just to inform you this. So let us start the solution. So we start by taking one such epsilon. Let epsilon be a positive real number. Immediately we use the fact that the sequence is a Cauchy sequence. Since, see there it has started. Some prayers and chantings, and along with that some drum. That's all, nothing much. Since this is a Cauchy sequence, there exists an integer m greater than or equal to m such that the distance between ai and aj is less than or equal to epsilon by 2. We choose to take epsilon by 2 in place of epsilon because this is also a positive real number, epsilon by 2. For all integers I and j greater than or equal to m. Okay. Now we are going to make the supposition that the sequence is not eventually epsilon close to L, what has been said here, suggested here. Suppose an is not eventually epsilon close to L. Okay. Now This implies many things, but it implies, many things in the sense this. Say you choose an integer k greater than or equal to m. The sequence not being eventually epsilon close to L means that this sequence is not epsilon close to L. Eventually epsilon close to L means after some stage which appears after this small m, the sequence, all of its terms are close to L. How close? The distances of those terms from L, all of them are less than or equal to epsilon. Not being eventually epsilon close to L thus means that such a stage can never be found. No integer k greater than or equal to m will be such a stage. In particular, in place of this k, we are going to take this m that we have got just now. So we are going to write like this. This implies in particular that the sequence an, where n starts from capital M, is not epsilon close to L. Now a sequence is epsilon close to L if all of its terms are epsilon close to L. So that means some term will violate that here. Thus, there exists an integer n naught greater than or equal to m such that the distance between a n naught and L is not less than or equal to epsilon, it is greater than epsilon. Now, for any integer n greater than or equal to m, we are now going to see a sequence of inequalities. Starting from this that we have found just now, epsilon is less than a n naught minus L, its absolute value. This one has got nothing to do with n, but now n will come. We will introduce n in this way, minus a n plus a n minus L, and we can use the triangle inequality here and write this less than or equal to absolute value of a n naught minus a n plus the absolute value of a n minus L. Okay. Now look at these two inequalities. Small n is greater than or equal to capital M and small n naught is greater than or equal to capital M. Both of them are greater than or equal to capital M. So we can think of them in place of I and j. So this difference, which is nothing but this, is less than or equal to epsilon by 2. So this sum is less than or equal to epsilon by 2 plus this other term. Hence, this is strictly greater, note that we have strict inequality here, is greater than epsilon minus epsilon by 2, which is equal to epsilon by 2, and this is true for any integer n greater than or equal to m. Thus, for every integer n greater than or equal to m, each one individually either an is greater than L plus epsilon by 2 or an is less than L minus epsilon by 2, which you can clearly guess these two inequalities come from the two possibilities that we have here. Either an minus L is non-negative, in which case this absolute value is an minus L itself. From that you get this, and if an minus L is negative, then this absolute value is L minus an. From that you get the second inequality. So now the terms of this sequence have been divided into two parts, those terms that satisfy this inequality and those that satisfy the other one. Based on this, we are now going to define two sets. Define S1 to be the set of all integers such that n is greater than or equal to m and such that an is greater than L plus epsilon by 2, and S2 is the set of those integers such that they are greater than or equal to m, and this is less than L minus epsilon by 2. So these are sets of integers, all of them are greater than or equal to m and they satisfy these inequalities. Okay, now we are going to suppose. Already we are under a supposition, keep that in mind. We haven't settled that. So inside that again we are supposing something. So we have to first settle this inner supposition and then we will come to the outer supposition, which is our original contradiction. Contradiction proof. Suppose both S1 and S2 are non-empty sets. That means we have integers like this as well as integers like this. So choose integers I in S1 and j in S2. Then I and j are greater than or equal to m. Since I is in S1, so for I this inequality will be true. Ai is greater than L plus epsilon by 2, and since j is in S2, Aj will be less than L minus epsilon by 2. Okay. Also, because I and j are greater than or equal to m, so from the place where capital M is coming, we have this absolute value of ai minus aj is less than or equal to epsilon by 2. Okay, now what can we conclude from these things? Note that, or let us write like this. From these we have what do we have? Epsilon by 2 is greater than or equal to, let's use the last one first, absolute value of ai minus aj. Now the absolute value of any real number is greater than or equal to the number itself. Now ai is greater than L plus epsilon by 2, and minus aj using this inequality is also greater than minus of L minus epsilon by 2. Multiply on both sides by minus 1 of this inequality and you will get that thing. Okay, and what is this term? L minus L, they cancel out, so we are left with epsilon. Which is absurd because epsilon is positive. You can divide, you see, so what have we got here? Epsilon by 2 is greater than, in fact strictly greater than epsilon. Because epsilon is positive, you can divide on both sides by epsilon, thus getting 1 divided by 2 greater than or equal to or greater than 1, which is false, which is absurd. Hence our last supposition is wrong. That is, S1 is empty, or now that is we should write we must have or S2 empty. Note that both S1 and S2 cannot be empty. That is understood now, because for every integer n greater than or equal to m, either this is true or this is true. So it cannot be the case that none of them is true. We have already proved that at least one of them is true. So that means either S1 is non-empty or S2 is non-empty. Assume first that what I said right now is not true. Either S1 is empty or S2 is empty. Assume first that S1 is empty. Then, so that means all the integers n greater than or equal to m are such that for them this inequality is consistently true, then an is less than L minus epsilon by 2 for all n greater than or equal to m. Remember that this what we have written just now, this one depends on the thing that we previously proved, that for any n either this inequality true or that is true, any n greater than or equal to m. Because of that we are able to write this. Now by exercise 548, so you just go to the statement of the exercise, or from the proof, what we are going to write here, that itself will tell you what the exercise is about. L is the formal limit of an this is less than or equal to L minus epsilon by 2. That exercise says that if all the terms of a sequence are less than or equal to something or greater than or equal to something, then the formal limit also is less than or equal to or greater than or equal to that thing. So we are using that here, which is, and this is less than L. But there is a problem. You may say that okay, all these terms are less than L minus epsilon by 2, but things are starting from capital M, not necessarily from small m, because that's where the original sequence started. Fine, but one can prove that the original sequence and this sequence where the index starts from capital M are equivalent. So if one of them has formal limit L, then the other one also has formal limit L. So for that we mention this. Note that is because we are using this exercise on this sequence. Not necessarily this sequence, but these two are equivalent and the formal limit of this one is capital L, so the formal limit of this one is also capital L. And now we have proved that L is strictly less than L, so this is not possible. The same contradiction or the same absurd inequality arises if instead of assuming that S1 is empty, you assume S2 is empty. So that means what? We have nowhere else to go. We are now forced to conclude that the original supposition is wrong. So our original supposition is wrong. That is, the original sequence must be eventually epsilon close to L. Thus, L is the actual limit of AN. L is the formal limit, but it's also the actual limit. So that completes the solution and also the proof of proposition 15. This proposition allows us to get rid of formal limits and replace them with actual limits. Okay, next. Exercise 7. Show that definition 6.1.16 is consistent with definition 5.1.12. That is, prove an analog of proposition 6.1.4 for bounded sequences instead of Cauchy sequences. Oh, okay, so it's that one. Recall that we have two definitions of a bounded sequence. We defined bounded sequences once for sequences of rational numbers, and then again we did it for sequences of real numbers. So the bounds that we used in those definitions, once it was a rational bound for a sequence of rationals, and once it was a real bound for a sequence of real numbers. Now, if one has a sequence of rational numbers and one says that it is bounded in the sense of this definition, that is in the real number definition, is it also bounded in the other sense? And conversely, we are now going to show that yes, that is the case. So when we are considering boundedness, we don't have to really use this definition or that one. We can use the latest one, and that automatically implies that even when we consider rational sequences, it's bounded in both the senses if it is bounded in only one sense. In one sense, I should not say only one sense. So let us see this. This one is very easy actually. Okay, let AN be a sequence of rational numbers. First, assume that this is bounded in the sense of definition the old one, that is the one formulated for a rational sequence. It's the easier among the two, so let us take this first. Then there exists a rational number k greater than 0 such that this absolute value, all of the absolute values are less than or equal to k for all integers n greater than or equal to m. Since k is also a real number, so this is a rational bound, so being rational it's also a real bound. So this condition, these inequalities automatically say that the original sequence is also bounded in the sense of the new definition. This is bounded in the sense of definition 6.1.16. Conversely, assume that the sequence is bounded in the sense of the new definition. Okay, then there exists a real number we can take anything, we can take r also, capital R, greater than 0. Actually in this definition r is allowed to be equal to 0 also, but if you can choose r equal to 0, then you can choose a higher bound also. Once you find a bound, then any number greater than that is also a bound, which you can see from here itself. Here k is a bound, any number greater than k, for that also these inequalities will be true if you replace that k by a higher number. So although in the definition 0 is allowed, but we can always choose a positive bound in the new definition, in the definition given for real sequences. So there exists a real number r greater than 0 such that an absolute value of an is less than or equal to r for all the indices n. Okay, now we proved a result corollary 5. Okay, now by corollary 5 for 13, there exists a natural number n such that n is greater than r. Recall, in one of the results we previously saw, we proved that the natural numbers are not bounded above. You find that in this corollary. Hence, this is also less than or equal to n for all n greater than or equal to n. So now you have found a natural number upper bound, or I should not say upper bound, a natural number bound for the original sequence. Now, being a natural number, n is also a rational number, and n is also greater than 0 because so is r, and n is greater than r. Thus, the sequence is bounded in the sense of the other, what is the number? Bounded 5, 1, 12. So as far as boundedness of sequences of rational numbers is concerned, both the definitions give us the same result. By both the definitions, a sequence is either bounded or not bounded. But note one thing, that if you have a sequence of real numbers where maybe some terms are not rational, then definition 5, 1, 12 is not applicable. Keep that in mind. Okay, next. Prove theorem 6, 119. It's that algebra of sequences, convergent sequences. Okay, many things are written in the hint. You can use some parts of the theorem to prove others. This in general is always, almost always true for results which have parts. Example, part B can be used to prove part C. Parts A and C can be used to prove part D. Okay, and parts B and E can be used to prove part F. Okay. The proofs are similar to those of lemma. Okay. Lemma 536. Then proposition 5310. If you want, you can go to these proofs and see what the author is trying to say here. And lemma 5315. For part E, you may need to first prove the auxiliary result. That any sequence whose elements are non-zero. Elements means what we are calling terms, the author is calling elements. And which converges to a non-zero limit. Is bounded away from zero. Yes. Okay. Instead of stopping in the middle of the solution, let me refill now itself. So the first thing we have to do is we have to recall the theorem. It is about limits of sequences, convergent sequences, but we will recall the parts. That I think will be, I think it will be better to, instead of recalling the entire theorem at once and then proving its parts, we will recall the parts as we prove them. And that will be much better. So let us start the solution from here. So what are we given? We are given two sequences, and those sequences, see here I forgot the fine. The index starts from m, starts from a general integer. Two sequences are given to us, both of which are convergent, and x is the limit of the first sequence, y is the limit of the second sequence. In part A, we have to prove that this sequence converges to x plus y, that is, this is equal to x plus y, or this is equal to this plus this. That's what we want to prove in the first one. Okay, so let us proceed with the proof. Since we have to start with epsilon. Let epsilon be any positive real number. Since x is the limit of an and y is the limit of bn, there exist integers n1 and n2 both greater than or equal to m, such that for all n greater than or equal to n1 and okay, so these are just the definitions of this limit, nothing else. Now n, which is the maximum of n1 and n2, is an integer because the maximum is either n1 or n2, such that n is itself greater than or equal to m, because both of these are greater than or equal to m, so their maximum is also greater than or equal to m. Now for any integer n greater than or equal to n, we have Okay. an plus bn minus x plus y. This is less than or equal to, using triangle inequality, an minus x plus mod bn minus y. Okay, now see, small n is greater than or equal to n, and n is the maximum of these two integers. So small n is also greater than or equal to n1, because capital N being the maximum of these two is greater than or equal to n1. Either it is strictly greater than n1 when n2 is greater than n1, and in which case capital N is n2, or it is equal to n1, which is the case that arises when n1 is greater than or equal to n2. So small n is greater than or equal to n implies small n is greater than or equal to n1. Similarly, small n is also greater than or equal to n2. So for small n, both this inequality as well as this other inequality that appears here, this one, both of them are true. Should we have written those things? Let us not keep any place for confusion. We have n greater than or equal to n1 and n greater than or equal to n2. In bracket we even write this also, since and hence Pn minus both of them are less than or equal to epsilon by 2. So this is equal to epsilon. So this absolute value of the difference is less than or equal to epsilon when n is greater than or equal to n. Hence limit of the sum is equal to sum of the limits. Next, in part B, we have product. Yeah, this one is not so easy or straightforward as this. Let us see its parts. Again, let epsilon be a positive real number. Okay. We first assume, so two limits are given. X is the limit of an and y is the limit of bn. So we first tackle the case where y is 0. It may happen. Assume y is equal to 0. Okay. Now, because our sequence an is a convergent sequence, it has a limit that is a real number, it is also bounded. We have already seen that convergent sequences are bounded, and that's what we are going to write. We write next. Let an be bounded by, it will be bounded by some positive real number, and the reason for this boundedness is corollary 6, 1, 17. Okay, so it is bounded by some positive m. Now there exists an integer n, m, k, let us take k, greater than or equal to m, such that Bn is, okay, I think it will be easier to understand if I write like this. This is less than or equal to epsilon divided by n for all integers n greater than or equal to k. What have we written here? You see, now that our y is 0 and Bn converges to y, so this difference can be made small. How small? We have decided to throw in the m here in measuring that smallness. Instead of just writing epsilon, we have written epsilon divided by m, which we can do because m is a positive real number, so epsilon by m is again a positive real number. Why exactly we are doing this, that will become clear now. So this is true for all n greater than or equal to k. This type of smallness of the distances between Bn and 0 will also start from some stage, and let that stage be k. Okay. Then for all n greater than or equal to k, we have mod an bn minus 0. This is equal to mod an bn, which is equal to absolute value of an times absolute value of bn. Now for any n greater than or equal to m, this thing is less than or equal to capital M, because this sequence is bounded by capital M. In particular, not just for any n, but for n greater than or equal to k, also this is true. That is, this first factor is less than or equal to m, and for such values of k, the second factor is less than or equal to epsilon divided by m, and this now becomes epsilon. So to get rid of this m, we divided by m here. So that's how we chose the number here like that. Okay. So now what have we shown? See, for any epsilon there is an integer k greater than or equal to m here, such that the absolute difference between an, bn and 0 is less than or equal to epsilon. So limit of an, bn is equal to 0. That's what we have shown. But 0 is xy because y is 0. So limit of a and bn is equal to xy. In this case, where y is 0, we actually have proved the result. Next, assume y is not equal to 0. We will now use the non-zeroness of y to again prove the result. Okay. Then if y is non-zero, there exist integers L1 and L2 greater than or equal to m. You may wonder how one knows from the beginning that such a value of epsilon has to be chosen here so that things get adjusted. The answer to that is we don't know. I mean, we first start with this calculation and then we see what we need and then we change this epsilon accordingly. That's how things progress. But when we present it as a solution, of course, things look very nice and it seems like we know beforehand everything what is supposed to be done. That is obviously not the case. Such that, for example, here also again we are going to take some things which it's difficult to guess when you see them for the first time. This is less than or equal to this for all integers n greater than or equal to L1, and this is less than or equal to epsilon by 2n for all n greater than or equal to L2. Now, in the case where y is non-zero, we have chosen to use the two limits in this way. That is, limit of an is x, limit of bn is y. So the differences between an and x and those between bn and y can be made small. How small? That is dictated by these numbers. First of all, note that since y is non-zero, absolute value of y is a positive real number. So here we are dividing epsilon by 2 times mod y. So the resulting number is again a positive real number. And this m already it is an upper bound for the sequence an, that is constant. This m is irrespective of whether the second limit y is 0 or non-zero, because it has got nothing to do with y. It is related to the sequence an, not bn. Okay. Now L, which is the maximum of L, once you see this type of arguments 2 or 3 times, you will start to realize what is to be done. This is an integer such that L is greater than or equal to n. This time we will not write all the things again, since L is greater than or equal to L1, which is greater than or equal to m. So those things are understood. For any integer n greater than or equal to L, we have n greater than or equal to L1 and n greater than or equal to L2. Now you know why, and hence, okay, now our focus is on this difference. We want to prove that this can be made smaller than epsilon. To get what we want, we are going to introduce an intermediate term, and that intermediate term is going to be minus any plus any minus xy. Okay, now first of all, when we apply the triangle inequality, we have this any plus any minus xy. Then you use more elementary properties of absolute value. We can write like this. Now, because of our choice of n and because of these inequalities, both these inequalities are true. So that means this term, okay, let's argue with one term at a time. This absolute value is less than or equal to m because this sequence is bounded by m times this value is less than epsilon divided by 2m plus this first factor is less than or equal to epsilon by 2 times absolute value of y, and here we have absolute value of y. So you can see that this becomes epsilon by 2 plus epsilon by 2, which is epsilon. Okay, so yes, this can be made smaller than or equal to epsilon. So in this case also we have proved this, where y is non-zero. Thus, limit of a and bn is xy. Okay, then in part C we have to prove this. Say C is a real number, then we have to prove this thing. Okay, you can see that it's almost like part B. The only difference is that instead of having a sequence, here we have constant C here, but you can think of it as a sequence, namely the constant sequence, all of whose terms or elements are constantly C, and apply part B, just that. So that's what the author was saying in the hint, that some parts follow from others. It follows from part B, in brackets we also write consider the constant sequence, all of whose terms are equal to C. Okay, so we don't have to do anything here. Then in part D, we have to prove this. an minus bn equal to x minus y. This can be done by applying parts A and C. Let us write specifically how this can be done. By part C we have limit of minus bn equal to minus bn can be written as minus 1 times bn. So in place of c you have this real number minus 1. So by part c this is equal to minus 1 times y, that is minus y. Now by part A this is equal to an minus bn actually is this. So by part A it will be equal to limit of an, which is x, plus limit of minus bn, which we have now shown, just now shown, is equal to minus y. So this is equal to x minus y. That is part D. We have two more, no, not two more, E, F, G, H. Oh man, okay. Okay, in part E, further hypothesis is there. First of all, it is assumed that each term of the second sequence is non-zero, and also it is assumed that the limit of bn, which is y, that is also non-zero. We then have to prove this, because all the bn's are non-zero, so their reciprocals can be formed, can be considered, and the reciprocal of y can also be considered. So we have to prove that the sequence of reciprocals of the original sequence, that is 1 over bn, that converges to 1 over y. Okay, for this one a little something has to be done, which has been given in the hint also. We have to prove that the sequence bn is bounded away from 0, if you can recall those concepts. Anyway, let us see how we can get this result. Since we start from the hypothesis that the limit y is non-zero, so there exists a real number delta greater than 0 such that 0 does not belong to y minus delta comma y plus delta. I hope that thing is not too much of a disturbance. Okay, so what is it that we have written here? You see, since y is non-zero, either y is positive or negative. So think of the point y on the numbered line. If y is negative, then 0 lies here to the right of y. No matter how close to y, it's to the right of y. You can then choose a delta sufficiently small, this much is a delta, such that y minus delta comma y plus delta, this open interval does not contain 0. Similarly, if 0 lies to the left of y, no matter how close, then also we can find an open interval centered at y. That is, we can find a delta so small that this interval excludes 0, it does not contain 0. This is always possible. Here we can see that geometrically, if you think of it for a moment, you can find an algebraic argument also exactly showing why this is true. It is so easy that I am not going to supply any more detail. That is, you just have to guess an appropriate delta and the job will be done. Okay, so this we are now going to use. We have sort of already y is somewhat, I mean it is close or far. These adjectives have no meaning when we are doing mathematics. If we cannot say how close or how far, it has no meaning, but still just qualitatively you can imagine the situation like this. Y is there, 0 creates a problem, so we have sort of put y inside a safe zone in which 0 is nowhere. Okay. Now, what is y? Y is the limit of Bn. Implies Bn belongs to, or let us first write about the integer, implies there exists an integer, what should we call it? Let us call it m, such that for all n greater than or equal to m. Why suddenly this limit implies this? It's because if you look at this relation Bn being in this interval, what does it mean? It is equivalent to this. Bn being in this interval is equivalent to these inequalities. Which in turn is equivalent to these ones, Bn minus y. This one we understand. this one comes directly from the limit. So equivalently this one is also true. I mean, these inequalities will start to become true from some stage, and let that stage be capital M. So accordingly these relations are also true from that stage. Okay. So we have now chosen capital M such that these things happen. Now there are two possibilities. Since 0 does not belong to this open interval, so either 0 is less than or equal to y minus delta, or 0 is greater than or equal to y plus delta. And y plus delta is less than or equal to 0. Accordingly, either we have this 0 is less than or equal to y minus delta, but y minus delta is less than bn. Why? Because bn belongs to this, so y minus delta will be less than bn. And note that bn is greater than this, which is non-negative, so bn is positive, so bn is equal to its absolute value. Okay, either we have this, or 0 is less than or equal to, if we multiply on both sides of this inequality by -1, then we get minus y minus delta. Now bn being in this interval satisfies this inequality. So that means minus y minus delta is less than minus bn. So in place of, we can write this less than minus bn. Okay, now just like what we had here, bn is greater than 0, now minus bn is greater than 0. So in place of minus bn we can write absolute value of minus bn, which is also equal to the absolute value of bn. So okay, oh, I think I see one small problem here. Zero not belonging to y minus delta. Okay. So this one exactly will not give me what I want. What I am trying to conclude from this is that all the absolute values of bn are greater than some positive real number, but this equality sign will prevent me from doing so, because y minus delta may as well be equal to 0, in which case we are just saying that absolute value of bn is greater than 0. Now that's not what I want. I want all the absolute values of bn to be greater than some positive real number. For that I am going to make a change here, and the change is that instead of considering an open interval, I am going to consider a closed interval. Question is it possible? Let us go to our little picture. This is our y, and say this is 0. Okay, y is less than 0, that means y is negative. What you do, you choose the midpoint between y and 0, which will be y divided by 2, and you base that midpoint to form your closed interval. That is, this will be y minus delta, y plus delta. Then 0 also does not belong to the closed interval, and the same thing can also be done if y is positive. I mean, since there is some distance between y and 0, so it's safe to choose a closed interval also that will not contain 0. So now when we say that 0 does not belong to this, there is no possibility for y minus delta or y plus delta to be equal to 0. Okay, so if we choose a closed interval here instead of open interval, then we don't have any possibility for these things becoming equal to 0, and we will have strict inequality here and ordinary inequality here. That is not a problem. There is no problem from this. Okay. Thus, for a moment I thought that it's game over, we cannot progress any further, but that small change saved us. Thus, there exists a real number eta greater than 0, which is either y minus delta or minus y minus delta, such that the absolute value of Bn is greater than or equal to eta for all n greater than or equal to m. This is what was suggested in the hints. Show that Bn is bounded away from 0. Okay. Now we can use, now see, we have found a lower bound for the absolute values of Bn for all n, and that lower bound is a positive real number. That is important. This lower bound will prevent Bn from becoming very small. In other words, it will prevent 1 over Bn from becoming very large, so that 1 over Bn, that sequence of reciprocals, will converge to something. Okay. Now, there exists an integer okay, I have everything here, so we have chosen m and then eta, so I can choose n greater than or equal to m such that the original limit is there. This is the original limit. This can be made small. How small? Less than or equal to epsilon times eta times something else, or this, for all n greater than or equal to n. Note that non-zeroness of y implies that its absolute value is positive. This is a positive real number, eta is a positive real number, epsilon is a positive real number. So their product is also a positive real number. And from this limit, these inequalities are true. So, for any integer n greater than or equal to n, we have, okay, now our focus is on this difference. This difference is, eventually it becomes this. Okay. Now, the numerator is less than or equal to epsilon eta times mod y. In the denominator, okay, this is greater than or equal to eta. So 1 over this will be less than or equal to, that is this thing, 1 over this is less than or equal to 1 over eta, and this thing stays as it is. So this now becomes epsilon. So this difference also can be made less than or equal to epsilon starting from this stage. Thus, so we have completed part E also. Okay, in part F, what was part F? In part F we had division. The same condition on Bn, that is y is non-zero and all the terms are non-zero. Then we have to prove this. This is equal to x divided by y. This we have to prove. In proving this, we are going to use part B and part E. By part E, we have one over y. So by part B, limit of an divided by bn is an times 1 over bn So now we can use part B. We know the limit of an, which is x, and we know the limit of 1 over bn, which is 1 over y. So their product will have the limit x times 1 over y, which is x divided by y. So this is part F. In parts G and H, let me say what they are. We have to prove this. In part G, we have to prove that limit of the maximum of an and bn is equal to maximum of x and y, and in part H, we have to prove that limit of the minimum of an and bn is equal to the minimum of x and y. Okay, so when you calculate this maximum and minimum, you have to do it term wise. Term wise means, for example, you have this. Let us take two arbitrary sequences, not necessarily convergent. Okay, I'm just simply giving one example: 0, 2, 1, 3, etc. Suppose here we have 0, 1, minus 3, 5, 0.6, 3, 1, etc. Then when we suppose this is our an and this is bn. Then when we calculate maximum of an comma bn, then here the terms will be this: 1 is greater than 0, so among them the maximum is 1. Here the maximum is 1 between minus 2 and 1. The maximum of 1 and minus 3 is 1. Maximum of 0 and 5 is 5. Then 2, 3, 3, like that it will go. Similarly, the sequence of minima can also be formed. So we have to prove that this sequence, not this example, I mean this sequence converges to the maximum of the two limits, and this one converges to the minimum of the limits. We are writing G and H together because the strategy is similar. One can show that for any two real numbers, A and B, maximum of A and B is expressible in this way, and minimum of A and B can be written like this. Which is not very difficult to prove. You just have to consider two cases: A greater than or equal to B and A is less than B. These are the only two possible cases. If A is greater than or equal to B, then what will happen to this? A minus B is non-negative, so absolute value of A minus B will be A minus B. So in this case, the first expression will be this, which is equal to A. So in this case, the maximum is A, which is true because it's the larger one. The exact opposite thing will happen with this expression. In that same case, the minimum will be B. Like that, you can consider this one also. Okay, so now These functions maximum and minimum have been expressed in terms of addition, division and absolute value. So we can write this. Also, it's easy to prove that limit of absolute value of an is equal to the absolute value of the limit. Hence, using the previous parts, it follows that and this completes the solution and it proves theorem 6.1.19. Okay, then exercise 6.1.9. Explain why theorem 6.1.19f fails when limit of the denominator is 0. To repair that problem, requires this thing, L'Hopital's rule, for which we can see section 10.5. We need the notion of derivative to state this rule. Okay, now this is extremely straightforward. It is because the equation becomes meaningless when y is 0. That's just it. We have been asked why this part fails, and that is the part where you have quotient of the terms of the sequence. So even when none of the bn's is 0, we know that the limit can be 0. One example is your classic one. Here none of the bn's is equal to 0, but the limit is 0. And lastly, we have another one. Show that the concept of equivalent Cauchy sequences as defined in definition 5 to 6 does not change if epsilon is required to be positive real. Instead of positive rational. More precisely, if a sequence an, okay, this time n varies from 0 to infinity, it does not really matter where the index starts, we have seen this before, and bn are sequences of rational numbers. Okay, show that an and bn are eventually epsilon close to each other for every rational epsilon greater than 0 if and only if they are eventually epsilon close for every real positive epsilon. So rationality or lack thereof of epsilon does not make a difference. In the definition, you can either choose epsilon to be rational or just real. Hint: modify the proof. It's again starting, but we are almost done. Proof of proposition 614. And the solution, actually we will not do anything. It's left to you because it is very easy, and as a guide you can see the solution to exercise 617. So there the solution ends. Don't really know how long this madness will go on. Anyway, so the set of exercises, current set of exercises is over. In the next video we will see a new section, extended real number system. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.